Introduce yourself.
Yes, I will introduce myself.
I will introduce myself. Guillaume Barraquand will give a talk about the lifestyle cumulants of the open KPZ equation. This is a joint work with Pierre Dussal. I guess I should thank all the organizers and the CMSA for welcoming us here and giving us the money to have this program.
See, nobody can pronounce your last name as well as you can.
You should learn.
We are trying.
So the talk is about the work we've just completed. It will be on archive, I think, next week, hopefully. It's about the open KPZ equation. So the open KPZ equation on a segment of length L. So it's the stochastic PDE or the height. So here X is in 0L. We have a Laplacian plus square of the gradient plus psi Tx is a space-time white noise as usual. So since I'm considering the equation on bounded interval, I need to impose boundary conditions. So the typical thing to do is to impose a boundary condition on the slope at x equals 0. We fix it to be u. The slope at x equals L, we'll fix it to be minus v. And here u and minus v are some boundary parameters in R. So as written like that, these boundary conditions do not exactly make sense because h locally behaves like a Brownian motion. So the precise meaning to that is given in a paper of Corwin and Chen from 2016. And the intuitive meaning is that h as a function of x it looks locally like a Brownian motion, and near x equals 0, it's a Brownian motion with slope u, with drift u, and near x equals L, it's a Brownian motion with drift minus v. And those conditions ensure uniqueness of the stochastic PD. So I will discuss mostly about these boundary conditions, and sometimes I will discuss the periodic boundary conditions. Ht0 equal HTL, and in all cases, we view HTX as usual in the Hopf transform sense. So this is the logarithm of d dx, where d solves the heat equation with multiplicative noise and appropriate boundary conditions. So that's I think that's the setup. So so recently I've been interested a lot in the stationary measures for this model and discretizations. But I don't want to talk about this next, and rather to talk about some attempt that we did with Pierre in order to understand what's next about the fluctuations. But we are at the very beginning, as you will see. So what's the situation is that we start at time 0 with some initial condition, maybe a flat interface, and then we let time evolve. So typically there will be a linear drift. So at time t, we will see something like that. So actually this picture is a bit wrong because typically the interface goes downwards, but it doesn't matter too much. And after time t, the distance between the initial profile and this one is about a constant time t, and this constant I will call it C1. So C1 can be computed. I think I will. Yes, I think I will give the formula now, actually. So starting from stationary initial condition. So there exists a unique stationary measure in the sense that the profile remains stationary up to a global shift. I will not say what this is, but starting from this initial condition, the expectation of h at time t and x equals 0 is exactly equal to this constant c1 times t, where c1 is equal to -1/24 plus 1/2 the log derivative in L of something which is convenient to see as a partition function. It can be, it's a normalization constant that arises in the probabilistic description of the stationary measure. But for this talk, I will not explain that. I will just skip to, I will just discuss formulas. And in terms of formulas, so we have a precise formulas for this quantity. So z uv of L is some integral over the imaginary axis of a certain function that I denote by psi, and psi will come back several times in the talk. So this function psi of w is equal to a product of gamma functions. So we have gamma functions of u plus or minus w. And when I say plus or minus, it means that I take gamma of u plus w times gamma of u minus w. I have the same thing with the other boundary parameter, v. In the denominator, I have gamma plus or minus 2w, and I have some Gaussian factor here. So that's my function psi. So you see that when you take derivatives in L, it just multiplies by a factor w squared. So instead of writing this log derivative, so this log derivative is derivative of z divided by z. I could have written this explicitly by just computing the effect of the derivative. It's not complicated.
Wouldn't you look at 0? You could look at other points. I mean,
yes, we could look at other points. If here I put x, I would have some correction that depends on x here, which can be computed. But the formula it would be a bit complicated than that. It's not particularly nice. So this result can be obtained in various ways. So the method is to compute that for a model which converges to the KPZ equation and then take a limit. And one has to argue that the limit holds for the expectation, but this can be done. So I obtained recently this formula on the log gamma polymer model, but actually formulas for A step have been known for a very long time. There is a paper of Tomohiro from, I think, 99, which computes this for the A step model, and then one can take a limit. The limit is a bit easier to take on the log gamma polymer model, which I did to obtain those formulas. So this is for the expectation. Of course, we're interested in what happens beyond the expectation. And then there is a question of how we scale things. So here we have the L is the size of the domain, and we may do different things as L and T goes to infinity. So if L is extremely large compared to T to the 2/3, then we expect that the type of statistics that we should see are the same as in full space. If we look in the middle of the domain, or in half space, if we look at the border of the domain. So these statistics are known. There is a very interesting case where L is of order T to the 2/3. There, the space-time process should rescale to some object which has not been constructed, which I would call the open KPZ fixed point. and one should see universal fluctuation results, but this is very difficult. It's very difficult to do the scaling and to study the fluctuations of the model. I have no idea how to do. So what we looked at with Pierre Ledoussal is to take L fixed and look at what happens as t goes to infinity. And this situation had been considered in the physics literature before, but I think that there are some nice answers which call for a better understanding of the mathematical structure and the full proof. And for the moment, I will state conjectures, but we don't have any full proof. We are actually quite far from it. I will explain why. So the first thing that one can ask beyond the expectation is about the fluctuations. So by ergodicity, there is a central limit theorem. So we expect that. So this is not proved, but I think it could be proved. I will tell you how. So we expect that h at time t x equals 0, say minus this constant c1 times t divided by square root t. So this converges to some Gaussian variable center with some variance. This type of result has been proved rigorously for the KPZ equation with periodic boundary condition. It was proved by Dunlap and Gu. And they actually remark in their paper that the proof would also extend to the open case, provided one proves some ergodicity result on the KPZ equation, which is proved in a paper of the 1 year later of Shalin Parekh. So essentially, the proof of the central limit theorem here is it's essentially in the literature, although I have not checked all the details, but following Dunlap-Gu, it's well understood. However, the question is, what is this constant C2? Okay, so the plan of the rest of the talk will be to explain some results. So I will have a conjecture for C2. But I will also explain a much more general structure. So we can consider all the cumulants together. We can consider the cumulant generating function. And the cumulant generating function has a very nice structure. And then I will explain how it can be obtained. The most direct way to obtain it is through something called the deformed matrix product ansatz, which was worked out in the physics literature, although it was worked out for ASEP. And then there is a question of whether the limit of ASEP gives the correct result. And with Pierre, we also worked, and actually we started with that, on a direct better ansatz approach in order to compute the limit of the cumulants on the KPZ equation with the boundary conditions. So here we use a method that was introduced by Brunet and Derrida from 2000. And this is here that there is some technical difficulties in order to go from the periodic boundary conditions to the open boundary condition. It's a bit more complicated. The deformed matrix product ansatz is based on work by, mostly based on work by Gori Sen, Malik Lazarescu, and Van der Zand. And that's around 2012. The structure of the cumulant generating function is particular, and that was something understood in an earlier paper of Sylvain Frolac a few years before. And there are also important works with Pasquier, but this one is this paper is the main one that we use.
In the approach of Dunlap and Gu on periodic, do they get the coefficient?
They get the coefficient written in terms of some Brownian bridges. So either you have to take 3 Brownian bridges or 2 Brownian bridges with some correlation between them. It's not obvious how to match this expectation of exponential functionals of Brownian bridges and the explicit expression coming from Brunet Derrida. This is still an open problem.
So is your sense that if you adapt their method, you'll get a similar expression, or?
Yes, I'm pretty sure that someone is working on this at the moment, and one should get some functional of processes related to the stationary measure. So it will be significantly more complicated, and matching with an exact expression will of course be also more complicated. So, but let me tell you what is the formula for C2. So in order to write what is C2 and also what are the higher cumulants, I need to introduce some operator. So I have a kernel KW prime, which is -2, and then I have two D-gamma functions. And here, the D-gamma function is the derivative of the log of gamma z. When preparing the talk, I hesitated to call this one psi because the way I draw my, this is the capital psi, and this is not the capital psi. So this is the standard notation, so I should not use it. And maybe this is not a very good one. Remember that this is the capital psi. So of course, K Kf of W will be the integral. So it will be an integral over the imaginary axis of Kw prime f of W prime on suitable functions f. And the conjecture for C2. So yeah, the conjecture. The conjecture, I will write it for when in the maximal current phase. So when U and V are positive, presumably one can also make analytic continuations and recover and we do this with Pierre in the paper. We can compute the value when U and V equals 0 or when U equals -V and these kind of things. But this analytic continuation is another thing that would needs to be argued, which is not totally obvious for the variance. So C2 depends on U, V, and L, and it can be written as 1/2 the derivative of 1 over the partition function. So the partition function here was the integral of psi. And here I have an integral of psi, k psi, plus psi squared. So that's the formula for that we found for the variance. And yes, so it is likely that it has a probabilistic interpretation related to some function of the stationary measure, but it won't be easy to find it. So where does this come from? For instance, I should try to explain where does this phi k psi plus phi squared comes from. Yes.
How easy is it to actually compute values of this?
You mean put them in a computer?
Yeah.
Oh, it works very fast. It was very fast, and we did it. So, for instance, if you plot it in function of u, there is something a bit strange. So at 0, it's first decreasing, and then it does something like that, and then it saturates to some value. So it looks like that. Yeah, it's very easy to plot. So this psi is some product of gamma functions. This because of the Gaussian decay, it decays extremely fast at infinity. So it's very well suited to numerical integration. And the k, so this doesn't decay as much, but because of the decay of the psi, there is really no issue with it. So yes, numerically it's very easy to compute. So in order to understand this structure, I will explain something more general, which is, so one can define a coefficient Ck as C1 and C2. So my Ck will be a limit, would be the draft time cumulant, so limit of 1 over T, and the case cumulant of HT0. So I claim that this has a limit, so all the cumulant scales as 1 over T. This is consistent with the fact that the law of large number occurs on the T scale, and so the large deviations should also be on the scale T. In order to write all the cumulants together, we can consider the cumulant generating function, the sum of s to the k over k factorial Ck. And this cumulant generating function has a parametric form, which is the following, and this is quite elegant. So S is the integral of a function u, which is for the moment unknown. And E of S is minus 1 over 24 times S plus 1/2 the integral of and so here, of course, in order to have a parametric form, I need to have some variable that still varies. And so there is a variable which is hidden in this function u. So here, this function u is the solution to some functional equation. U of w equals minus 1/2 the log of 1 minus 2 zeta psi of w exponential k u. So that is the key functional equation that allows to compute all the cumulants. So of course, at first, it's not completely obvious that everything here is well defined. For instance, if there are in principle, one should say something about solutions to this functional equation. But the way in which this statement is still makes sense is that one should see this as both sides as power series in the variable zeta. So here I have a variable zeta, and as this zeta varies, the function u varies, and s and E of s vary. And that defines a function. It will define a function in a unique way. If we understand properly this identity here, so one should understand this as a power series. So it means that one should view u of w as a sum of zeta k uk of w. And hence, this identity is actually a collection of many identities, which allows to define by recurrence the UK. So, yes. If you look at UK on this side, it will be written in terms of the lowest order UK on the right-hand side. And that allows to define U in a unique way. So for instance, if one does that, one finds that U1 is psi. And that's why the function psi arises in the first cumulant. One finds that U2 is psi times k psi plus psi squared. And that's why this quantity here appears in the second cumulant. And U3, I will not write it. I mean, it can, of course, be computed, but it starts being a bit more complicated for higher cumulants. An important remark. an important remark is that in the periodic case, the same result holds with psi of W being just the Gaussian factor. And K has to be replaced by K over 2 or something like that. So K is changed slightly. And the important thing is that for psi, we take just the Gaussian factor. Okay.
The form of this is for when U and V are both positive, where U plus V is positive.
Yes. This is when U and V are both positive. So I've just erased the psi, but when yes, they are poles at U minus U and V and minus V, and so when U and minus U and V cross 0, there's some poles change location. So yes, everything is done for U V positive. So in terms of results, I also wanted to explain the large scale limit. So maybe I should not give the formula, but just the idea. The large scale limit, so we can consider the limit of all these cumulants and the cumulant generating function as L goes to infinity. And in order to get meaningful parameters in the limit, we have to scale U as some U tilde and U parameter divided by square root L, same for V. And then the cumulants C1, so C1 is always minus 1 over 24, and then it behaves as 1 over L times a cumulant sigma C tilde, and all the other cumulants, they scale as L to the K minus 3 over 2 times C tilde K. Yes. So this power of L here is not really surprising, and these cumulants here are the same as for open TASEP. So in the open TASEP or open ASEP, so any model in the class actually one can compute the large time cumulants, and these are not universal. These control the large deviation rate function of the model, and of course it depends. It varies model to model, but when we compute the large L limit of those large deviation functionals, well, if one accepts that there is some commutation of limits that holds, what one is actually looking at is the large deviation functional of the KPZ fixed point, and that's why all the models in the class should have the same cumulants in that limit L to infinity, following the same scalings. So what one can verify here is that the scaling is correct, and one obtain expression for the C tilde. So here the expressions are simpler. So the C tildes are encoded by some cumulant generating function E tilde of S tilde, and I still have a parametric form for E tilde of S tilde, but this one does not depend on a function U, which one has to solve. So the parametric form is already explicit. And one can compare with earlier works. Maybe I won't say much more about this. Yes?
A naive question. So if you look in the middle of your interval and you take the two sides to infinity, you get a full volume, infinite space model. What happens to your formula? Do you get cumulants of the Tracy-Whittem distribution?
I don't think so. No. No. So one obtains the. No. One. Okay. So we have one model, and we are looking at cumulants when L is fixed and T goes to infinity. And so, okay. So we let T go to infinity, and then L go to infinity. And what we obtain are the large time cumulants of the KPZ fixed point. So the H so yes, we obtained in the limit the C tilde k corresponds to the limit as tau goes to infinity of 1/tau times the kth cumulant of h tau 0, where, or actually here I could replace tau by any x, where this capital H is the KPZ fixed point. But it's in the large time limit for KPZ fixed point with fixed size, and I don't think that one recovers any quantity that occurs in full space. Okay, so that's I explained roughly why one can compute the scaling limit. The results simplify, but these are essentially known, and these are supposed to be the limiting cumulants of the open KPZ fixed point. So how to obtain all this? How to obtain in particular this functional equation? So as I said, we computed the cumulants in two ways. Actually, we started with the hard way. So we started by adapting the method of Derrida and Brunet and Derrida, which is complicated. And then we compared with what happens using this deformed matrix product on that, and we realized that the two methods were giving the same result. So now I will first explain the simpler approach, which is the deformed matrix product on that. So we consider a set on L sides. We have injection and ejection boundary parameters, rates, denoted alpha, beta, gamma, delta, as usual, and the particles, they move with rates 1 and q left and right. So a configuration of the system is encoded by a vector eta in 0, 1 to the power L. And I will consider, so in order to analyze the process, one can consider the Markov matrix Q eta prime. I think I will not write this Markov matrix. That's the Markov matrix encoded the non-diagonal coefficients or the rates from eta to eta prime, and the diagonal coefficient is minus the sum of the non-diagonal coefficients. What is important is that one can decompose Q as some Q0 plus Q plus Q minus, and these ones, Q plus and Q minus for me are the non-diagonal coefficients when a particle enters or exits the system from the left. So Q plus would be when a particle enters the system. Q minus will be when a particle exits the system. So in a sense, I just consider those coefficients, because when I will want eventually to compute the number of particles that have entered the system. And then with this decomposition, I define the deformed Markov matrix Q mu as Q0 plus exponential mu Q plus exponential minus mu Q minus. So now this is not a Markov matrix anymore, because I have multiplied some of the non-diagonal coefficients by exponential mu, exponential minus mu, without changing the diagonal coefficients. But exponential mu, exponential minus mu are still positive. So I can still apply the...
It's just what if, I mean, Q plus and Q minus just refer to two boundaries, right? I mean,
Q
minus and Q plus are living only at the two boundaries.
Yes.
Yeah, okay.
And yes, maybe these are not the best notations. I just mean that I multiply in my Markov matrix the non-diagonal coefficients corresponding to a particle entering the system. I multiply the coefficient by exponential mu, and I do exponential minus mu for the other ones.
Sorry, this is for left boundary only.
Sorry?
This is for left boundary.
Yes, this is for the left boundary because what I'm interested in is not to know at a given time how many particles are in the system. This is encoded by the stationary measure. What I want to know is the history of the process, so it's integrated current. Really the out of equilibrium thing that I want to understand. So this is so considering this Markov matrix allows to compute E of mu, the limit as t goes to infinity of 1 over t log expectation exponential mu n t0. So here NT0 is the integrated current. The number of particles that have entered the system from the left minus the ones that exit from the left. So we count only at the left. And this is the Perron-Frobenius, the largest eigenvalue of Q mu.
Yeah.
So that's a very old trick. I don't know where it comes from. I found the paper of Herbert, Leibowitz and Spohn from '98, which already uses this in the context of ASAP. And I don't know about earlier references, but at least it dates from that. Yeah, so the way it works, is that one can write something. So this expectation here from some initial data eta 0, exponential mu and t0, it can be written. So it's just a problem of linear algebra. It can be written in terms of the exponential of q mu. So what we get is the vector, well, all the components of 1 transpose times exponential t q mu times the vector that I denote delta eta 0. So the vector which puts coefficient 1 corresponding to the initial condition and 0 elsewhere. And so if one takes the log of that, so provided this is not orthogonal to the Perron-Frobenius eigenvector, one obtains the Perron-Frobenius, the largest eigenvalue. So one just needs to check this non-overlapping condition. And I think that this can be argued from the fact that the process is irreducible, but I have not seen a complete proof of that actually. I think this can be fully justified. Okay, so one is reduced to computing the largest eigenvalue of some explicit matrix. And this is something which can be done by various methods available in the physics literature. So the one that was employed by Gorissen, Malik, van der Zand, and Lazarescu is to use a deformed matrix product on that. So in principle, the matrix product on that is used to find the top eigenvector, but it can also efficiently compute the eigenvalue. And the way it's done in that paper, it's perturbative. So they compute it. They compute the expansion in the Poisson series in mu of E of mu, order by order. So in order to get to order mu to the k, they use some matrix product on that made of k-fold tensor products of the usual deformed matrix product of the usual matrix product on that for A set. So it's a bit technical, but one arrives at the expression that I've mentioned for the cumulant generating functions. I should also mention that this the fact that all the cumulants can be packaged together and expressed in terms of the solution to some functional equation. This comes from some earlier work by Prolak. So Prolac had another method to compute the cumulants in for T-SEP on the torus, I think, more combinatorial, and by working out his quantities, he figured out a bit by chance this functional equation, and then that functional equation was recovered using different means by different authors. So there is this group of people who worked out the deformed matrix product on that and found similar functional equations. And then there is also a paper by Lazarescu and Pasquier, which also re-explains how the functional equation comes from ASEP by computing the top eigenvalue E of mu of this matrix Q mu, not using matrix product ansatz, but using the standard beta ansatz.
I mean, it's always a functional equation for the generating function, right? And you know.
So the generating function will be mu equals something, E of mu equals something. Actually, it takes a form similar with what I've explained before. So now it's a contour integral around 0 of some function w of z, dz over 2i pi z. And here you will have something similar, 1 minus q, something times wz. And this w satisfy a functional relation where, so w of z will be minus 1/2 log 1 minus zeta. Now we don't have the psi function, but some function f, and k w of z. So of course the k here is the k for ASAP. It's the operator is different from the one in the limit, and this f is also a bit different. So instead of having gamma functions, we have products of many Kubo-Sharma symbols. Yes, this is. So I think I will not give more details on this because I want to give a few ideas about the other method, the method of Derrida and Brunet. Brunet and Derrida, sorry, I don't know why I say Derrida and Brunet. So this is a method using better on that. So now one can also work directly at the level of the KPZ equation. So one thing that is unsatisfactory by working on ASEP and taking a limit is that we know that ASEP converges to KPZ, so the typical fluctuations converge. But it's not clear that the large deviations of ASEP should converge to the large deviations of KPZ. So it's really not clear actually that the cumulants should converge. So in principle, this method is extremely non-rigorous. It's a bit better to work directly at the level of ASEP, of the KPZ equation. So this is what we first did. So our cumulants. So these are large time cumulants of the KPZ equation. So by definition, they correspond to a limit as t goes to infinity of exponential s. So that's just the definition of the cumulant generating function. And here, let's imagine that s is some integer. Then what we are computing, the exponential of h is something that I call zt0 n to the power n. So if s is an integer n, I'm computing this kind of quantity. So in other terms, I need to compute moments for all n and even for non-integer n and take the limit as t goes to infinity. And this is something which is conveniently done by the beta ansatz. So here, of course, it's not mathematically rigorous, but it's interesting to see that it will give the same limit. And there is still some interesting math that I will try to explain there. So
Let me just ask one question. I mean, interrupt you. I mean, so the answer is for the delta Bose-Gas, right?
Here, yes.
Yeah. And so what are the precise boundary conditions for the delta Bose-Gas? I mean, so this is the wave function.
So these are the. So we have Neumann-type boundary conditions for H.
Yeah.
So they
what is
become
the boundary
Robin type
condition?
for Z,
Yeah.
and our eigenfunctions should have the same Robin type mixed boundary conditions.
Ah.
But
No, go ahead. Let's see.
I don't have a lot of time, so maybe I will skip a bit. So I think that most of you know a bit the story. So we have eigenfunctions of the beta-ansatz, psi lambda of x. This can be written as a sum over symmetrized permutations of the symmetrization of a coefficient a lambda times the plane wave. So lambda I xi. The lambda I parameterize my eigenfunctions. And so a lambda have some explicit expression, which I will not write, but maybe I should. So the a lambda, so the a lambda depends on the left boundary parameter, and my beta equation will depend on the right boundary parameter. So of course, both boundary parameters in the system should enter into the game. So the lambdas satisfy the beta equations, which are that the exponential of 2 lambda alpha L is equal to B minus lambda alpha and then I have a complicated product. So this is a complicated equation, and for all alpha, the lambda alpha should satisfy this. So of course, there are many solutions, but what we are interested in is the eigenvalue associated to the Liebniger operator, which I have not written, the eigenvalue associated to this eigenfunction, which is the sum of the lambda I squared. So we need to find the maximum of this quantity over solutions of these beta equations, and figure out an expression in N which becomes analytic. So that's what one needs to do in order to compute the cumulants.
You think we just need to compute the bound state, right? Is that what you're saying?
Yes. So actually, we don't even need the ground state. We just need the eigenvalue associated to it.
Yeah, no, okay, that's what I mean. Yeah.
So we can. So at this point, we can forget about the expression of the eigenfunctions. We just assume that this form a complete basis, or at least the ground state has this eigenvalue. So yeah, in the end, we are reduced to considering solutions. So the lambda i's are complex. We are considering solutions to this equation, and we take the set of solutions which maximizes this, and this is a quantity that we want to analyze. So the idea of Derrida and Brunet and Derrida, I don't know why. The idea of Brunet Derrida is so it looks really tricky, and at first one does not understand the intuition. So I will just tell you quickly how they do, and then I will try to give some intuition behind it, how it can be understood from a simpler limit. So what they do is that they introduce a function L of z, which is the sum alpha 1 to n of exponential lambda alpha z. So far this makes sense. If we can compute this thing, the second derivative of z at 0 would give us the sum of the lambda alpha squared. So that makes sense. But however, this quantity does not solve any particular nice equation. So what they do is that they multiply the coefficient by rho alpha, and the rho alpha are the product for lambda different than lambda alpha minus lambda minus or plus c, something like that. So we look at the exponential lambda alpha z correctly weighted by some weight which is convenient to use the fact that our lambda alpha satisfy beta equations. And they managed to find two equations for lambda z. These two equations don't have unique solutions. Actually, they cannot have unique solutions because some solution corresponds to other states than the ground state. But in the papers of Brunet and Derrida, they pick some special solutions which they expect correspond to the ground state, and it seems to be correct. So first, there is one needs to come up with this, and here it's also not obvious to find. So there is an integral equation satisfied by L and some differential equation corresponding to the beta equation. So both seem very ad hoc and are a bit hard to understand, but it's very creative. They managed to do it and to pick the right solutions. What becomes more technical in the case of the open boundary condition is that, so one of the equations is essentially the same, except that we have more symmetries in the set of beta roots that we have to deal with, but this is not too complicated. The issue comes from the second equation, the one from corresponding to the beta equation. Because of these terms here, which are not present in the periodic boundary condition case, the boundary conditions here, the beta equation is a bit harder to study, and this is more technical. And so that's why using this method, we can compute the first cumulant, the second cumulant, and the third cumulant, it becomes, so we can get some expression, but then it becomes very difficult to match with the other approach using the deformed matrix product on that. So far we have matched only the first two cumulants. And so before I stop, I just wanted to give a bit of intuition behind this kind of transform here and the equation that they should satisfy. And it's something which is explained in the paper of Brunet and Derrida. Which is that one can play with the parameter C, which is the strength of the noise in the KPZ equation, in such a way that the psi lambda, they are eigenfunctions of the operator delta plus C times the sum for I less than J of delta xi minus xj. So one can put a parameter C here. In the periodic case, it is possible to show that the lambda I corresponding to the ground state, they behave approximately as, if I remember well, square root C times hi, where the set of hi are the roots of the Hermite polynomial Hn of x. So the orthogonal polynomial of degree n, which is orthogonal with respect to the Gaussian measure.
But are you saying you have to pick a fixed C or?
You let C go to 0.
Ah, okay.
So, and in that very simple limit, but which is still instructive to understand how to be able to compute something as the sum of the lambda x squared. The lambda I go to roots of the Hermite polynomial. So how to compute the sum of the square of the roots? So this is in principle not very. So this is not complicated at all. There are many ways to check that the monic Hermite polynomial. So first coefficient by definition, by my definition, is x to the n, and then the next one is n choose 2, x to the n minus 2, and one can compute the following ones. So of course, this is n choose 2. But imagine that I wanted to compute not just this, but sum of hi to the k, and have some way to do this more systematically. So then that would be, it would be natural to introduce the function q of u, the sum. So u now is some parameter, and I introduce hi of u, and then this quantity contains all the moments, all quantities like that. So if I take the case derivative at 0, at u equals 0, I would compute this. So knowing this function would allow me to compute this for all k simultaneously. So I don't know actually what are the techniques to do this, but the technique which is suggested by Brunet and Derrida is to work in Laplace. So instead of considering q of u, one considers q of u exponential minus u x du. And then here, the integration over u, so if I replace q of u by its expression, the integration over u can be performed. And if x is large, this gives hn prime of x over hn of x, which I can call f. And you will see something nice appearing. So something, at least the computation is really in the spirit of what Brunet and Derrida are doing, and so that's why I want to explain this. So now there are differential equations satisfied by the hn. The differential equation is hn minus h xn prime plus n hn, I think, for 0. So this leads to differential equations for f very directly. We get f prime plus f squared minus xf plus n equals 0. And then one can try to work a bit with this thing. So of course, knowing q or knowing its Laplace transform is more or less the same thing, right? So what we need to know is this function f. And this function f satisfies a rather simple differential equation. And then what Brunet and Derrida do is that they want to essentially know this for all n, not necessarily integer. So they assume that this f of x has some expansion in n. Like n to the k, fk of x. Now it becomes a bit formal, but if you plug this here, you will find a simple expression for f1. So you find a very simple differential equation, which is easy to solve. You get something like du exponential minus ux exponential minus u squared over 2. You can also solve for f2. You get also something which can be solved in Laplace. So there is some function f2, which is explicit, which one can figure out to write f2, etc. And one after the other, you can compute the fk's. Just some remark which I don't know what to do with it, but this expression for f says that q of u is n exponential minus u squared over 2 plus n squared times some function f2 of u plus O of n cubed. And so this means that at first order, we have this. So this essentially means that it essentially means that 1 over n times the sum of the exponential h alpha u at first order in n behaves like behave like exponential minus q squared over 2, as if in the limit n goes to 0, so of course in the limit n goes to 0, these H alpha are not perfectly well defined, but it's as if there were some roots which distribute according to a Gaussian distribution along the vertical axis. So we see, so we started from the roots that are orthogonal with respect to the Gaussian measure on the reals, and as n goes to 0, we have some sort of virtual roots which are distributed as some Gaussian measure on the vertical axis, and I don't know if there is anything more general there, or if it's only for the Hermite polynomials. And but this is a question that is actually asked by Brune and Derrida, and I don't know the answer. So I think, oh, I should stop here. Thank you.
Two approaches to study the same problem. You see how much are they kind of equivalent? You could check the up to 2 cumulants.
Yes.
Right?
Yes. So in the approach by the deformed matrix product on that gives a clear answer, and yes, it gives a clear answer, which looks like other models. The approach by Derrida, Brune and Derrida is much more ad hoc, and we managed to naturally see the psi function coming. It really comes from how the beta on that equation translates in terms of that function L. We can, by deduction, find the correct psi. However, there was also a kernel K that arises in the formula. And in the Brune-Derrida method, we see actually it's natural to introduce some kernel, but the kernel we introduce is different from the one by the other approach. So then, even for the second cumulant, there is a non-trivial work to match, but it matches. So this we did it very, very precisely. It matches, and at the level of the third cumulant, we also compared the formula, and it seems to match. But there are very annoying issues of poles that one has to. It's a bit annoying to do the matching, and we have not done it for the third cumulant. I believe that it matches, but it's not done. And the way it's not obvious is because the kernels are different.
Matrix product approach contain information of the equation?
Yes. Actually, in a sense, the top eigenvalue of the deformed Markov matrix could also be computed using a standard beta-ansatz approach. So it would be a deformation of the beta-ansatz on ASEP. But here as well, we believe that the top eigenvalue is expressed in terms of the beta roots, and so one could actually approach the problem this way. Also in the deformed. So what I call deformed matrix product ansatz, I should maybe call it deformed Markov matrix approach, because the top eigenvalue of the deformed matrix can be computed by different ways. And we took a limit of a work based on deformed matrix product ansatz, but then there were also works by Pasquier and Lazarescu, where they compute by beta ansatz the top eigenvalue of the deformed matrix. So there is also, of course, a connection.
You described for ASAP and KPZ how it works, but are there special cases where it actually can be made rigorous? For instance, if you wanted to just prove something about the open KPZ fixed point, you would go through a simpler model.
Yes.
You think that's
I can. Yeah, so yes, I have a. I think that there is an open. So I'm wondering if the large time cumulants in the periodic Shor process. So the simplest way would be to look at last passage percolation. So go to zero temperature limit. And then there is a model of last passage percolation on a, let's say on a cylinder, which correspond to the periodic Shor process, except that the rates vary. But in a certain limit, where when this periodic Shor process becomes singular, and it takes an infinitely long, and the path, the optimizing path in that last passage percolation model become infinite, I believe that the cumulants that one should see this way, so one should look at exponential of mu times lambda1. So lambda1 would be the top coordinates of some periodic Shor process, take the expectation, take the log, and then look at the limit when some parameter, so there is some parameter, you could call it u, or I don't know how it's x called in a certain way. As it goes to 1, I think this should have a limit, and I'm wondering, it's not, probabilistically, it's not entirely obvious that it yields the same limit, but I suspect it does. However, I don't know how to compute that limit and to make it, I mean, of course, in principle, there is a Phelan determinant for the law of this, but still, I don't know how to compute this limit and write it in a way that would be similar with the parametric equation that we expect. So I think that would be this is the approach I have in mind.
If you look in the half space, then one has a half space Donald Shor. That's right. And you can extract the distributional limits from this, at least at the boundary. Your approach with either deformed matrix ansatz or beta ansatz, does that also give something there?
It should give the upper tail large deviations. But yeah, I think it should give the upper tail large deviations, but yeah, I don't know. I have not thought about this much. And when I say it should give, is assuming a lot of non-rigorous things, but I don't know how much can be made rigorous.
Finish the talk. Did the talk.
Oh, yes, yes.
Thank you again.